Okay, is the light level all right for you guys? You want to try to turn any lights off, or is that all right? Yeah, maybe if somebody wants to flip or dim some of those lights, it might be helpful.
That's better.
Okay, great, thanks. So let's review. I've got a couple questions up on D2L. So again, with the questions, these are just kind of broad. It's like, hey, I'm having problems with recommended problem 9, number 7, stuff like that. The more specific your question is, the easier it's going to be to talk about. So if we have time at the end, I'll try to address a couple of these where it's like, hey, this problem's giving me issues, but if I don't know specifically what the issue is, it's a little bit harder to talk about. This other one, please solve 1617 and 1637. I'm not going to do that, right? We can talk about setting it up, but I'm not going to go through it and fully solve the problem. Because again, the problems on the exam are going to be strongly based off what the recommended problems are. And we can talk about setting it up, but I'm not going to provide the full solution to it. So we'll get to those at the end if we have time to talk about them. But in the meantime, if you guys want to tell me, if we want to make a list, we only have an hour and a half, but if we want to make a list of things that we want to talk about, again, the more specific the better, but it's completely up to you. So yeah.
Yeah, I was looking at 1616, and I would like to know how to get M.
How to get M sub C. Okay, great.
I actually have 3 M.
Well, let's get some of the ones and we'll come back to you in just a minute. What else do we want to talk about? Yeah.
We do 16.9, I took a question how to draw it, and there's 2 cuts like that. Do we input the shear and moment and just draw one diagram?
Okay.
Or do we separate it down? Because like the other problem is 1 cut, each place of your shear and moment.
So number of cuts, number of diagrams, things like that. Okay. Hey, yeah, Evgeny?
So how to find shear force in row 1633?
1633, shear force.
And the same problem, could you explain how to get, the maximum possible shear and how do you calculate that?
Yeah, so actually, that's a good point. With 1633 and with the very last influence line problem, which is 1637, so we didn't get to the material that basically says, draw the influence line diagram and then tell me what the maximum results are. We just ran out of time. And so that aspect of it is not going to be on the final, right? So you could, fair game to ask you to draw the influence line diagram for either 1633 or 1637, but the last part of the problem saying, hey, now load this up with dead load and live load, whether it's a distributed load or a point load, that's not going to be on the final. I'm happy to talk about it, but I think that it would be better conversation offline because you won't need to worry about it for the final. I wish we would have gotten to it. It's the real value of influence lines, but you'll see influence lines in 325, and Dr. Schumacher will go over that. Yeah, Ryan.
Really, for any of these, as we go in chapter 16, can we go over the correlation between the shear values that you get in your influence lines and how that kind of correlates with the shear to the moment diagrams? Because I know like some of those things that we got when we got like certain values for the negative positive influence lines, they kind of went with the angles that were created to find the moment diagrams, and we went through that kind of quick.
Okay. Yeah, so you're talking about how do we actually calculate the value of like a moment diagram based off the fact that like the difference in the angle has to be 1. Yeah, so kind of the oftentimes it's going to be the relationship of the angles, and so we create like a inverse of the sum of the inverses to calculate that. So I think it's maybe a bit more specific to the moment influence line, but so for moment influence lines, how do you calculate the heights? So moment influence lines, how do we calc the height of the value? Yes?
That's visual integration.
Yep, visual integration. Yep. What were your other 2 questions that you had?
Yeah, it was 1617 V8.
1617
V8.
V sub A, okay.
And 1633 18, 16.
Okay. So this is plenty to get us started. Hopefully we can get through most of this. Again, if not, I'm going to hold office hours. I don't know. Did I post office hours for next week? I can't remember if I did or not. No, I don't. We just have, yeah, I've got to figure that out. I might open up some office hours on Monday. If I have time, I'll open up office hours on Monday. If not, I'll be available by email as well, or by appointment. But we'll get through as much of this as we can, and then I'll rely on, either by appointment or if I can open up some office hours on Monday, I'll do so. So let's talk about 16.6 first. That's the first one that we had. So 16.6. Let me look up the diagram so we can talk about it. Okay, so 16.6 isn't on the list of recommended problems. So was it, you just want to talk about that problem in general?
I had a hard time going through homework. I looked at that one and it's similar.
Okay, yep, so I just don't have it in front of me, so you're going to have to describe to me what it looks like. Okay, great. Okay, so we have an overhang beam. We have A, B, C, and then we have a section cut 1. And we're given some dimensions here. So we have 10 feet to the section cut, another 20 feet to point B, and then 10 feet after the section cut. Thanks, Abraham. Appreciate it. Okay, so and specifically the question was the moment at C, right? Okay, so when we're creating a influence line diagram for the moment, what's kind of the procedure for that if we're going to do it the graphical method? Yeah.
Draw a couple moment, right?
Yeah, we draw a couple moment applied to what, basically? Yeah, like a moment release. And so here, when you deal with like the ends of the beam, or if you're talking about like doing it over a support, that often adds a little bit of extra complexity to it. So here, I'm basically adding a hinge at C, but there's nothing to the right of it, which is okay. It's possible to have a hinge out there, there's just nothing really connected to it, which is okay. And then, just like you mentioned, then you're gonna draw a moment couple. And really what that moment couple is doing is it's trying to rotate the left side of the hinge counterclockwise, and it's trying to rotate the right side of the hinge clockwise. And then all that we do is we try to figure out, well, if the left side is trying to rotate counterclockwise, what would the shape of this beam be that comports with all of the boundary conditions, the support conditions that we have on the beam? And so what are the boundary conditions for this beam?
0.
Yeah, 0 deflection at A because it's a pin, so that's a hard point. That point cannot move. And where else? Yeah, B. And we know that with our influence lines, they're always straight lines. And so we need to figure out a way to like rotate this side down in a way that the remainder of the beam, there's no joints or anything else here, the remainder of the beam passes through A and passes through B. So is there any way to rotate this beam on the left for that to happen? It's impossible, right? If this ABC, if that is straight, it needs to remain straight. And A can't move up or down, B can't move up or down, so it has to remain straight. So all of the rotation is going to occur on the right-hand side, but there's no beam on the right-hand side. So here it's kind of like a phantom rotation. I mean, there's some, rotation here, but like the beam on the right of C has a length of 0. And so it's basically telling us that there can't be any internal moment at the end of the beam. Now, this is where the graphical method, the visual method, I wouldn't say it's like impossible to do it, but there's also an easy way. I mean, if you're ever concerned like, well, this doesn't make any sense if we would just have a single like zero diagram, like a constant zero value for the influence line for the moment at C. If you're like, well, that doesn't make a lot of sense to me, what could you do to kind of make sure that that's correct? You can start calculating it, exactly right. What you could do is you could put a point load at A, make a section cut at C, and figure out, well, how much of that force causes a moment at C. And if I put the support right here, the point load right here at A, well, I'm only going to have a support reaction at A, no other reaction over here, no moment over there. So I know that at least the value right here is going to be correct. Right? I know that quantitatively, if I were to put a point load at A, do all my support reactions, and then do a section cut right at C, and determine what the internal moment is, it would be 0, and that's why I would get this point right here. Well, likewise, same thing at B. If I put a point load there, I'm going to verify that there's no moment at C caused by that point load. And then, yeah. Okay.
It's actually this one.
Okay, great.
Sorry about
16, 16, not 16.6. Okay, well, no problem. Well, this is still a good one to discuss. Let me draw this one down, and then we'll talk about it in a second. So pin, roller, we have an internal moment release. We have an internal moment release. We have a roller and a roller. And so it's A, B, C, D, E, F, and the lengths are 80, 20, 40, 20, 60. So 80, 40, 20, oops, 80, 20, 40, 20, 60. Okay, you can pick that up whenever you want. So let's finish talking about this problem here. So same thing, even if I put a point load all the way at C, when I run my free body diagram and I make a section cut at C, I'm going to find that there's 0 internal moment as well. So I guess the bigger picture kind of lesson from this would be, if you're dealing with maybe a location, whether it's at the beginning or the end of the beam, or over a support, or maybe even like in problem 1616, where it's right already at a hinge, well, then you can always rely on doing some spot checks with the quantitative method. So this is like what I've been talking about in class before. If you go through and solve a problem, and you're like, well, something's wrong, I think. And then you say, well, how can I verify or check my work? Then you go through and you do a section cut. You show me with an equilibrium equation that, well, this answer that I got, it has to be wrong because, look, I just proved that it's wrong. I did a check. I got different values. So this is why it's wrong. I can give you a lot of partial credit for something like that. Yeah?
If you did a section cut between B and C, would the moment just jump up to 1?
So good question. So the question is, if I was talking about instead of point C, what if we were talking about, let's make a new point like D or something like that? If that's where my point of interest was, how would it change my influence line diagram? Would it just jump up? Would it look maybe something, or jump down, look something like that? Would that be correct? Exactly right. Yeah, this is what it would look like essentially for the shear at point D, but for the moment at point D, it's going to look like this. And basically this line is going to have a 1-to-1 slope is what's going on. So this would be the influence line for the moment at point D. But then you see what's happening is this point is moving left, it's moving right. Once it gets all the way to C, because this is a 1-to-1 slope, well, there's no distance between C and the end of the beam, and therefore it just ends up being just a single point right at 0. Yeah, question?
Between the couple moment, is the moment going to jump up to the height of H?
So
down? It's going to go up, right?
you're talking about here?
Yeah.
Yeah, so here the point would be, you're talking about, is it going down or is it should be going up? Is that what you're saying?
In between the couple moment?
Well, so
Up the height of H.
don't think about this as like necessarily a like couple moment. This is just a reminder to us saying, look, in the influence line, it wants to try to rotate clockwise on the right of our point of interest, and it's trying to rotate counterclockwise on the left. That's all this is doing. Don't think of this as an actual moment that like causes a jump up or a jump down or anything else like that. Just think of this as like reminding ourselves what direction is trying to rotate on either side of the point of interest. So there wouldn't be any like jump here necessarily.
Not even for like moment graph?
Well, that's what this is. This is the influence line for the moment at D. And so there's not a jump there. So that's why, again, this is why it's different than a moment diagram, right? The influence line is not the same thing as a moment diagram. This couple moment, that's really just reminding us, well, when we're doing the visual method, it's trying to rotate the right side of our point of interest clockwise. It's trying to rotate the beam counterclockwise to the left. So there's no jump there. That's just kind of reminding us, yes, it's trying to rotate down here. It's trying to rotate down over here. Now, whether it can rotate down depends on what the boundary conditions are, because you'll notice here, right, and even if we were focusing on D, it wants to try to rotate the portion of the beam to the left of D. It's trying to rotate it down counterclockwise, but it can't because there's no way to draw this beam rotate it downwards and not have a deflection at B and or not have a deflection at A. There's no way to do it. Okay, so let's talk about this problem, which is 1616. Same idea, just a more complex beam, but also unique in the sense that we're asked to find the moment at C influence line diagram. And if I gave you a problem like this on the exam, you could basically solve for it without doing much. Because what's going on at C? C is a moment release. Oh, I'm sorry, okay. But now that I look at problem 616, it's actually asking for the bending moment at B. So let's talk about both of them. The first one's really easy to deal with. The second one's going to be a little bit trickier. But if I was asking for the influence line diagram for the moment at C, you wouldn't need to do any calculations. You wouldn't need to draw anything. You would simply say, look, there is a moment release at C, and therefore the internal moment being passed to that point is 0. Therefore, the influence line diagram is going to be just 0 the entire time as well. So I'm not going to ask you a question like that. Well, I mean, I guess now that we've talked about it, maybe I could, but it would be not worth a lot of points because you should be able to, do that without doing any manipulation to the system. Now, the moment at B, let's talk about that. So is that more in line with what you wanted to know, the moment at B? Okay. Yeah, so let's talk about the moment at B. So same kind of a thing where now we're talking about adding another release above a support. So with the previous problem, we were adding a release to the end of the beam, which kind of caused maybe some conceptual issues. Here we're talking about adding a hinge above B. So MC is really straightforward. At B, I'm basically adding another moment release. So now we have the one that I just added to make the influence line diagram, but this beam also has 2 other moment releases as well. And so in this situation, I'll draw what I'll call like the direction of rotation that we're trying to impose. Now, the question is, for the left of that point of interest, can it rotate? Is it possible for AB to rotate counterclockwise? There's no way, because let's draw all of our boundary conditions. No deflection at A. No deflection at B. That's still valid. I added a hinge up above the roller support, but that doesn't mean that it gets to deflect now, right? That is still a valid boundary condition. It's not affected by the internal hinge that we added. And likewise, point E can't deflect, and point F cannot deflect. So what does the influence line look like from A to B? Just straight 0. Yeah, it's just going to be a straight 0 between A and B. So 0, 0. This is the influence line for the moment at B. What about, well, how about this? What other portions of this beam can we also like set as 0? Like there's no way that it could move. Yeah, DEF, this section right here, it can't rotate. It can't displace and it can't rotate because I have 2 hard points at E and F. And so from D to E to F, it's also going to be 0. We know that for sure. This is all going to be 0 at D, E, and F. So what we're really dealing with is, can the beam rotate downwards somewhere, like to the right of B, and then get back to D? Yeah, so is that possible? So if I tried to rotate this downwards like this, how would it get back to D? Yeah, so just like this. C is a hinge. It can displace as long as the left side rotates and as long as the right side rotates. So I could get back like this, basically. And so this is going to be point C. Yeah, question?
About the hinge changes direction? Or hinge?
Which hinge? We have 3 here now at C. Yeah, so here the reason is that the reason it can change the slope is because it's a hinge. Right? A hinge means that the displacement on either side has to be the same. So if the right side goes down 1 inch, the left side has to go down 1 inch as well. But the rotation can be different one side versus the other. That's basically the definition of a hinge. It means deflection compatibility, but not rotation compatibility. Yeah, Hannah?
So there wasn't a hinge at D, it would be because E and F can't deflect, so it would stay a straight line.
Yeah, exactly right. So if there wasn't a hinge at D, C, E, F would have to be a straight line, and therefore we wouldn't be able, then there wouldn't be any rotation between B and C. Exactly right. Mm-hmm. Yeah.
And then it's H distance, right? The triangle?
Yeah, so let's talk about that next. That kind of goes along with Ryan's question as well, too. So how do I calculate the height, like what is the value right here of this influence line diagram?
You just use the components of the triangle. So like H over 20 plus H over 40 equals 1 over H.
Yeah, so I think that we need to first draw like where is that, like the difference in slope that we're talking about. It's not between here and here. The difference in slope that equals 1, or like, you know, I've written it out as like 1 radian, but let's just think of it as like the difference in slope between the 2 different sides. It's not focusing on point C. It's not talking about the left side of point C and the right side of point C. What point is important? Yeah, point B is where the slope of this line and the slope of this line, the difference has to be 1. That's what it's saying. And so I'll still draw it like this, but you could also think of it as like a slope of like 1 to 1 like that, because there's 0 slope in AB. That means that all of the difference in slope has to be taken up in BC. Yeah, question?
How do you get to that conclusion? Because I still think that we should just focus on those 2 triangles. So how are you deciding that?
Yeah. So how I'm deciding on that is just kind of based off what it says in the exam packet. So it says rotate the beam on either side of the point of interest so that a unit rotation exists between either side. And so this, when we say point of interest, we're talking about the influence line is focusing on one specific location in the beam. That's the point of interest. So we don't get to decide where the unit rotation difference exists, like where along the beam it exists. It always has to be the difference on either side of the point of interest. So it's because of this number 3 rule that we have. And I just noticed here that there's only 4 rules for the moment, and it said 1, 2, 3, 5. There's not a missing number 4, so keep that in mind. Yeah?
In this case, never mind. Okay, got it. Sorry.
No worries at all. So here, B is our point of interest, so that might even be a good thing to put in your diagrams. Like this is our point of interest because we're focusing on the moment at B, that is the one location on the beam that we're essentially calculating the results of. That is our only point of interest. That's why it shows up over here. Now, the different locations along the beam that we use to create this graph, that's talking about where the point load is, not different points of interest. And so in this case, if the slope is 1 to 1, then it's really easy to calculate h, because here we're basically saying the relationship of 1 to 1 is the same as the relationship of h to 20 feet. And so in other words, h is going to equal 20 feet. So the height right here is going to be 20 because this little triangle right here with a slope of 1 to 1 is the same as the ratio of this larger triangle.
So does it work also, because in the book also talks about once you find the shear value at that point, just multiply that value times the distance, and then you get the height.
Yeah, you know, I think maybe that's what Ryan was talking about as well too. So I've actually never used that method. I've always, it may well work, and it's fine by me if you use that methodology. That's not the way that I've learned or taught it in the past, but if it works, that's fine by me. The way that I would do it for a moment influence line diagram is I wouldn't, if I didn't have to solve for the shear at B influence line diagram, I wouldn't go to that trouble just to make it easier to calculate like the height of this triangle. I would simply rely on the definition in the exam note sheet that says, look, the difference in rotation between the left side of the point of interest and the right side of the point of interest has to be 1, or what we call a unit rotation. So it's not 1 radian, it's just a unit rotation. It's basically kind of a placeholder saying that the slope is going to be 1. I would just use that definition in some similar triangles to calculate the heights. But if there's a easier way for you to do it based off what the book is telling you to do, or like another shortcut, completely fine by me. No problem at all. But honestly, yeah, I usually don't teach that. I believe that it's in the book. I've just never gone to the trouble of teaching it. Okay, so let's talk about 16.9. So 16.9. Actually, that's another one that's not in the recommended problem. So if somebody wants to describe it to me, I'm happy to draw it up here as well. Yeah, great. Okay, so this is a double overhang beam. And we have one section cut just to the right of the left support. We have another section cut 2, somewhere in the span in between. And we have a couple different dimensions here. We've got 6 feet, 10 feet, 6 feet, and 12 feet. And we have A, B, C, and D. And here it's asking us for the reaction at B, RBY. It's asking us for shear 1, 1, bending moment at 2, 2. Yeah, so it doesn't really matter, but yeah, it should be a pin. Yep. For vertical loads, for transverse loads, it shouldn't make a difference, but good.
Statically determined doesn't matter for us.
What's that?
If this were statically determined, or sorry, not statically determined, but unstable, it wouldn't matter.
Yeah, so as far as the horizontal dimension, like stability goes, it wouldn't affect our analysis because all of the point load that we're talking about is always transverse to the beam. So the horizontal stability would only be an issue if you had a horizontal load applied. Yeah, I mean, I wouldn't give you an unstable beam just because it would add some like confusion potentially, but as far as would it actually have an effect, the answer would be no. Yeah, for transverse loads, it wouldn't cause any issues. Okay, so here, whoever sponsored this, which of these do we want to talk about? I can guess which of these is going to cause the most problems. I'm guessing it's V11. Yep. So V11, I've drawn it a little bit to the right of the support, but I think that in the call to question, it basically says, look, section cut 1-1 is like an infinitesimal distance to the right of support B. So, and this is another situation where if the visual influence line, like the qualitative method, if you're having problems applying it, you can always, resort back to checking your work with the quantitative method. Now that doesn't mean that you have to do this whole problem in the quantitative method, doing section cuts and moving the point load across the beam. You're not going to have enough time to do that on the exam. But what it might do is if you're looking at this with the qualitative method and say, well, I'm not sure like what's going to happen on the left side. You're like, well, I'm pretty sure I know what's going to happen on the right, but on the left, maybe I'm a little bit confused. Well, just put a point load at A, make a section cut just to the right of the support at B, calculate the internal shear, and that will tell you what the value should be at A, right? So you don't have to move a point load to A, to B, to either side of the section cut, to either side of the section cut, to C and to D to really figure it out. But you might be spot checking one location using a free body diagram, equilibrium equations, if you're not completely comfortable with the qualitative method. And again, if you can show me, hey, I did this qualitatively, I think I got it wrong and I can prove it because here's a free body diagram of one specific loading location that shows me that there's an error in my influence line. That would go a long way for partial credit. So, but let's do the qualitative method just to kind of talk about it. So here, what is the rule for the shear influence line diagrams? Like how do I draw that qualitatively?
It needs to be one gap.
Yeah. And the one gap is caused because we add a shear release at our point of interest. So here if we're talking about V11, I'm going to add a shear release, and then it's going to want to go which direction on the right? Does it want to go up or down? Yeah, it wants to try to go up, and on the left it means it wants to try to go down. Now, just like what we've talked about before, that's where it wants to go. The question is, can it? And the can it question gets determined based off what the boundary conditions are. And so at B, no deflection. At C, no deflection. Yeah?
Also, before you move on, sorry, so do you put a hinge?
Oh, great question. Yeah.
Then that's my question.
Okay, yeah, great, awesome. So section cut 2 is only important for this analysis right here. You only put in the release at your location of interest for that specific response that you're looking for. So here, you're only applying one, you're only doing this work one at a time for whichever, subparts you've got for the problem. So you're only going to put the shear release at B, at 1-1. You're not going to do anything to section cut 2 until you're analyzing moment 2-2. Yeah.
And I can find RBY using similar triangles. That's my shear diagram, right? RBY.
You're saying that you can calculate RBY, like the influence line values that.
Yeah, I can use similar triangles.
Yeah, I mean, so for RBY, the procedure would be you take that support and then you move it upwards a unit value, and then you're exactly right. Like you would get, if you're doing RBY, and this is just kind of a side thing, you would move up a value of 1 at the support. So this is B, I move it up 1. Then I need to draw the rest of the diagram that agrees with the support conditions. So I've moved up B. B is displaced up 1. It's still free to rotate because it's a pin, but it still needs to pass through point C. So at point C, it needs to have a value of 0 at C. And so this is going to be my RBY influence line. And so that's why like this value over here at A is going to be larger than 1. This value here is going to be negative. And we need to use similar triangles to figure out those values. But yeah, a really good question about, well, you give me a problem, Evan, and it has 3 different types of responses that you're looking for an influence line for. Do I put all of those, do I do all of those at once? Do I move up the support at B1? Do I apply the shear release at section cut 1? And do I apply the moment release at section cut 2 all at the same time? And the answer is no. You do them each individually. And so with the shear 1-1, if we're just doing that analysis right here, the right wants to go up, the left wants to go down. which of these are, which of those are viable? Are they both possible? Is only one possible?
The left-hand side stay and the right-hand side go up.
Yeah, and why does the left-hand side stay where it's at? Yeah, there's a support right there. It can't deflect. And the fact that this is like an infinitesimal distance away from each other, that basically means like this point can't move. It's not going to rotate or anything else. That point can't move up and down. So as a result, this is going to stay. This side is going to move up that full value of 1, and then it still needs to agree with this. So it's going to go up, then it's going to go down straight through C. It has to be a straight line, then you get a negative value over here at D.
So between A and B, it doesn't do it, or it stays at 0.
Well, actually, I'm sorry. It's not going to displace up and down. Let's talk. Yeah. So let's finish the discussion about A and B. So it's not going to move up or down right there. But what needs to be true about AB? Well, yeah, it's going to go through 0 at B, but the slope is the other criteria that we have here. Exactly right. All of the slopes on either side of that shear release has to be the same. So this is kind of a tricky one. So if the influence line to the right of section cut 1, it goes up a value of 1, it comes down like this. All right, and this right here is a value of 1. This slope here has to be the same as the slope in section AB. So we know that B has to be 0, so the only way to get it to work is to draw a line that looks like that. And so is that right? Like, how could that be true? It looks really weird. How could you, I mean, is there any way to check and make sure that that's true? Put a point load at A, and then make a section cut just to the right of B. So what you would do is you would, to check your work, you would put a point load at A. You would have your support reaction here, which you would need to calculate using a global free body diagram. Then you'd have your section cut here, and then you need to calculate V. So this is B sub Y. So if you solve for B sub Y using the global free body diagram, and then you made this section cut and made this free body diagram, the question would be, is V going to be 0, or is it going to be some positive value? Because those are kind of the two options that we've talked about. And that would be a really easy way to kind of check your work. Now, how about this? When I have a point load out at A going downwards, is the support reaction at B going to be the same as that point load? It's going to be different, right? Because you get that lever action. And so I can tell you right away that V is not going to be 0 in this situation. So this is going to make more sense than if this was a straight line. So you can always go back, if there's any segment of the influence line that you're, unsure about, do a free body diagram, solve for the support reactions, make a section cut, and then you'll be able to verify whether or not those values are correct or not. Yeah, Ryan.
So in this problem, it's stating that that section cut 1 is supposed to be right there at the pen.
It's just to the right. Yeah.
So that's why it's showing up at 0.
Yeah, exactly.
So if there was a set distance that it was away from the pen, and we put a point load there, then you would see from section AB to that distance, it actually would rotate.
And go negative between B and the section cut. Exactly right. Exactly right. Yep. So that's another good way to think about it is, well, here it's giving us the extreme case where the section cut is right next to the support. What if I just moved that section cut a little bit to the right? Well, then that's going to be up here positive, a little bit negative, then back up to positive and down. We're used to that. All that we're doing is we're just moving that point a little bit to the left, which means that this point where it then jumps back up, this point gets closer and closer and closer to 0. So then that way, kind of looking at the more, common case and just moving that point is another way to vet the answer. Okay, let's talk about 1633. So this is one of those problems where I said, again, we didn't get to the content where we're actually applying the loads. I will just talk about the influence line generally, but with problem 1633, you're not going to be asked to do the second part of the problem. You would only be asked to find the influence line. And so actually 1633 is a super easy influence line. It is just a pin and a roller. And the section cut of interest is right through the middle. And so the influence line, here it's talking about, let's see. It's asking for shear and moment, like how do you maximize the shear and the moment on section cut 1-1? All that you would be asked to do for a problem like this would be find the shear influence line diagram for this and find the moment influence line diagram for this. And the second part of the problem, just to kind of talk about it, it's if you're trying to find the maximum result of either shear or moment, basically you're just putting the loads where they cause like the maximum effect, which is what the influence line is showing us. So for example, the shear influence line diagram for the shear on section cut 1 is going to look like this. So that basically means, look, if we're trying to maximize the shear here, I only want to load up one side, like one half of this beam, because if I load up the other side, the other half, these two areas kind of counteract each other. If I load up the left, I get positive shear. If I load up the right, I get negative shear on section cut 1. So that's where the pattern loading comes into play. The dead load, we don't have an option. It all has to go on there. The live load, we would only load up one side. Yeah?
So, in the convention, the shear on the left side needs to go down, the one on the right side needs to go up?
Well, I mean, this is simply showing that if you put any loads from here to here, it will cause a positive shear on this section cut right here. That's, oh, I'm sorry. I see what you're saying. Yeah, I just drew this upside down. I'm sorry. Yep, thank you. I was just talking about how they're different, but you're right, that this would be the correct signs to use. But either way, same idea applies. Dead load, we don't have a choice. It has to be spread out all the way across. If I want to maximize the effects, I want to load up all of one side and none of the other as much as possible. Now, live load, we can do that. Dead load, we don't have an option. But the actual mechanics of how we would then, say, apply a distributed load to the right side and calculate how much shear that causes, we're not going to get into that calculation. It's really easy, and so it'll be fine for you to learn it in 325. But it basically just involves multiplying areas together. I mean, it's a really easy calculation. But I mean, a fair conceptual question would be, you know, where should I put a load to get the maximum effect? Which isn't asking you for the magnitude of what the shear is going to be, but like where should I put a point load to maximize like the positive shear on section cut 1? Well, you would be putting that point load right here because that's the largest value of the influence line on the positive side. So a question like that conceptually would be fine, but I wouldn't say if you have a 25 kip point load, what would the value of shear be on section cut 1? I'm not going to make you do those calcs. Same thing with the distributed load, but just conceptually, where should the point load go to maximize its positive shear effect? That would be a fair question. All right, let's talk about, okay, so moment influence lines, how to calculate the height. So we had a kind of a quick discussion saying that the textbook might talk about another tool that will help you calculate the height of the moment diagram based off the shear influence line diagram. Like I said, I'm neither familiar nor do I teach that method. It may be in your book. The fundamental, like the most rigorous way to go about it, so moment, influence line, geometry, or height, the most important thing is that tool or that rule that we know that the slope on one side of the point of interest versus the slope on the other side of the point of interest, like the difference in those slopes has to be 1. And that's kind of the fundamental rule. And so here's just a schematic kind of diagram. If that's our point of interest, we know that the difference in slopes is equal to 1. Now, your book basically calls it a unit rotation. again, it's not like 1 radian. What we're really saying is that the slope difference between these is equal to 1. You can approximate that using radians, and it all works out. But I know that a couple of you I've talked to have said, hey, that conceptually just doesn't really make a lot of sense because 1 radian is like 180 degrees. That doesn't make a lot of sense to me. So think of it as like the difference in slope between this line and this line has to equal 1. Now, that's the easiest way to work. And if you get a triangle that looks like this, just like we talked about in class, drawing a nice big diagram to kind of help you with that is going to be helpful. And the one example that we did in class, we kind of broke down and we said, look, for this triangle here, I've got some angle on the left of the triangle, some angle on the right. If I break down, if I have the lengths, like the geometry of my beam, let's say this is length 1, this is length 2. I can do some further kind of breakdowns as well. I can say that, well, this angle, this unit rotation here, some portion of it is theta L, some portion of it is theta R. And so I have kind of 3 equations that I combine together. I know that theta L plus theta R equals whatever this unit rotation is. Just essentially a placeholder. I mean, I get it, like if we're talking in radians, 1 radian doesn't make a lot of sense, but we're just basically saying the slope on the left plus the slope on the right has to equal 1. If I know this, then I simply need to be able to plug in, well, how do I calculate the slope on the left? How do I calculate the slope on the right? Well, that's really easy. The slope on the left is simply going to be equal to whatever this unknown height h is divided by length 1, and the slope on the right is going to be equal to the height divided by L2. And then if I combine all 3 of these equations together, I only get one unknown left, which is simply h. And there's multiple ways to solve for that. In this case, for this specific scenario, the height is going to be equal to the inverse of the sum of the inverses, 1 over L1 plus 1 divided by L2. This is some basic algebraic kind of manipulation of that equation. That's how I could calculate the height. There are other ways to do it as well, but this is probably the most familiar way for me to go about it. Now, the issue is that this diagram right here isn't always going to be the situation that you see. So we just saw an influence line a second ago where our point of interest had 0 rotation on the left and then all of the rotation on the right. So in this case, that was really easy. In that case, the slope on the right, the unit rotation on the right, it was all on the right. There was none on the left. And so in that kind of a situation, if I'm trying to find, let's say, like the height right here, I'll call it h, and this is L, I'll just call it L. Well, it's really easy here because we know that think of this in terms of like slope, 1 to 1 equals h to L. So in other words, h is simply going to be equal to that length. So these are really the 2 primary ways that you're going to see a moment diagram a moment influence line on either side of a point of interest, either some slope on the left, some slope on the right, or no slope on one side and all of the slope on the other. Those are really the 2 most complex ways that we can look at a moment influence line on either side of a point of interest. So it just takes a little bit of practice, but it shouldn't be, I can't really throw too many other kinds of scenarios at you. It's always going to look like one or the other of these. Now, again, the other type of, well, yeah, we'll just leave it at that. Any questions about this kind of procedure? Remember, it's fundamentally different for moment influence lines than it is for shear influence lines, right? For shear influence lines, we're almost always talking about similar triangles. Here, I do kind of use like a similar triangle step for this example, but it's not the core of what we're doing in the problem. All right, let's talk about visual integration. Great. So all of these so far have been Chapter 16 questions, which is great. But let's talk a little bit about visual integration, which is really relevant to Chapter 9. So visual integration, your book only shows it for bending moment diagrams, but it works for any other kind of multiplication of one function by another. So we have an equation that says that 1 times some deflection is equal to the integral over the length of little m times big M all over EI. And so we'll just call this the bending deformation. So I'm ignoring shear, axial, spring, stuff like that. I'm just saying, what is the deflection due to bending? Well, the fundamental equation that we have is the integral over the length of the virtual moment equation times the real moment equation divided by EI. And this can work out well. If it's easy to find the moment equations, this is a fine way to do it because you're always dealing with a definite integral. So you can plug it into your TI-36X, like no problem whatsoever, get an actual number for it. But your book also says you can simply sum up the values, and let me make sure I use the right variables here. It also tells us that you can sum up the product of the area underneath the real moment over EI diagram times the value of the virtual moment at this distance x tilde, or x bar, I'm sorry. So what it's saying, if it equals the summation of A sub m over EI times m of x bar, what you do in this situation is you take the moment diagram, which you might be able to determine just visually based off the loading that you see on the beam. So let's talk about a situation like this. So let's say that your real moment looks like this. Let's say it's a linear function, it looks something like this. And let's say that your virtual moment looks something like this. So this makes the most sense when getting these diagrams. You can do it kind of visually, really quickly. You don't have to make a section cut. It's relatively simple loading. And if I want to get this equation out of these diagrams, there's a couple different things that I need to do. So the first thing that I need to do is I need to actually modify this diagram to be the real moment divided by EI. So for example, that means that like this value up here, as an example, would be like, say, positive 10 kip inches divided by 29,000 KSI times 1,000 inches to the fourth. Just an example. That's the moment in kip inches, E in kips per square inch, and I in inches to the fourth, just by way of example. So this area right here is relatively equal to, easy to calculate. Here the area underneath the M over EI diagram is simply going to be equal to 1/2 the base times the height. Let's go ahead and say that the length of this is like 120 inches or something like that. So if I were to plug in the values, it would be 1/2 the width, the length of that triangle is 120 inches, and the height would be 10 kip inches divided by 29,000 KSI times 1,000 inches to the fourth. So that's the area. It's just a triangle, and so calculating that area is really easy. And now I need to multiply this value, A over MEI, times some property of this virtual moment triangle. And the way that we do that is we need to find M of x bar. Well, x bar is defined as the x value for the centroid of the real moment diagram. And because this is a triangle, the centroid of the triangle is going to be equal to, B divided by 3, which in this case is 120 divided by 3, so it's 40 inches. So it's saying at this location of the centroid, at 40 inches from the left side of the diagram, give me the height of the virtual moment diagram. And so this is M x bar, it is simply equal to m at x equals 40 inches. And so if this is just a triangle, so let's say like the height over here, if we're talking about the virtual moment diagram, this might be, let's say like 120 or something like that. If that's 120, and I want to figure out what the height is right here at 40 across, well, that's just a similar triangle kind of a calculation. If this is 40 inches right here, then we can say that m of x bar, that ratio divided by 40 inches equals 120, which is the value on the right-hand side of that virtual moment diagram, divided by the length, which is 120 inches. And in this case, I would get m of x bar simply equals 40. So in this case, I would simply take this value and multiply it times this value up here. So I would just take those and I would multiply whatever this product is times this, and that would give me the value. That would give me the same value as if I integrated the product of those two equations. Instead, I've just done it graphically. Now, the way your book does it, I think, is a little bit goofy to a certain extent, because you don't need to divide by EI in this diagram right here if you don't want to. I mean, you can divide by EI pretty much anywhere. You could divide by it for this diagram. You could divide the virtual moment by EI if you wanted to, or the way that I prefer to do it, the way that I learned how to do it, it would be the area of the real moment diagram times the value of the virtual moment at x bar, all divided by EI. It's the same exact thing. If you're dividing by EI in the real moment diagram or the virtual moment, or you're taking the product and dividing by EI, it's still just a scalar division. It doesn't matter where you necessarily do it. So completely up to you. Now, if you don't feel comfortable with that method, I mean, the pitfalls that I see here inevitably are that students will either try to, instead of calculating the height of this triangle at a specific location, they'll try to do the area of the virtual moment diagram. That messes stuff up all the time. Oftentimes I'll see people just calculate the centroid at the wrong location. I mean, there's a couple pitfalls here, but it can be a lot faster than trying to do the product and then taking the definite integral of it. So this is completely up to you. I'm not going to make you do one method or the other. The other pitfall that I see would be if you go to the exam packet and you go to the properties of these shapes, another common issue that I see is that people try to, let's say, use one of these shapes here for like a cubic graph. These are parabolic shapes, so x to the second power, and inevitably I'll see people try to use this in situations where it doesn't really apply. Likewise, like here, this point here is the vertex. That has to be the point where the parabola is changing direction. Likewise here, and if it's not, then these graphs also don't apply. So something else to keep in mind. All right, so any other questions about visual integration? Again, so much stuff in this class, there's multiple different ways to go about it. This, visual integration might make sense to you. I'm not going to make you do one way or the other on the exam. Okay, so let's talk about 1617 next. So 1617, another influence line diagram problem with the added complexity of it already has a shear release in it. And so this will help kind of test our understanding of the procedure. Here we have what would otherwise be a propped cantilever beam. There's a roller at A. There's a fixed support at the right at C. But in between at B, there is an actual shear release. Not one that we've added for purposes of the problem, but like a shear release that exists. So this would be the deflection on the left and the deflection on the right of that shear release don't have to be the same. But the rotation on the left and the rotation on the right do. That's what a shear release means. So it is free to move at that shear release relative to either side. But if one side rotates, the other side rotates as well. So it could look like this, it can look like that. It can't look like this, it can't look like this, because both of those, the slope on either side is not the same. So slope has to be continuous, deflection does not. And we're specifically asked here to find the effects at section cut 1-1, and specifically, I believe the shear at section cut 1. Okay, and we need some dimensions here as well. So 30 feet, 15 feet, 30 feet. All right, so if we're talking about the shear on section cut 1, what do I need to do? Put a shear release there. So we'll get 2 shear releases. One of them actually exists, and one of them we put in there just for purposes of making the influence line diagram. So this is a farce, right? This doesn't really exist. We're putting it into the beam to help us draw the shear and moment influence line diagrams. This one does not, does really exist physically in the system. So now I put that the right side wants to go up and the left side wants to go down. And now we've got to figure out, well, which of those can actually happen. If I try to move the right side up, the left side down, can it happen? And then what would the final diagram look like? So let's draw our boundary conditions next. So what are my boundary conditions for the beam?
A.
Yeah, what about A? No displacement. What else? C. What about C? No displacement. Yeah, importantly, no rotation because it's a fixed support. And that's the key to this problem. So you can start from whatever side you want. If we start from A, well, I know that A can't displace. The question is, does it go straight, or can this move down? Well, we know that this point can move down. But it would be okay if it moved down. Whether or not it does, we'll have to figure out a little bit later. But like, it could move down. There's nothing keeping it from moving down. But we kind of have to stop there because we can't conclusively say that it can move down. Because for this point on the left to move down, what needs to happen to this portion of the beam? Well, it has to rotate, right? Yeah, if this point displaces downwards, it has to rotate. But the question is, can it rotate? And so we need to kind of go to the right side of the beam to figure that out. So at C, can it rotate? No. That means that at B, can it rotate? No. It has to be a straight line. And this starts out as horizontal. Here, it stays horizontal. And so it has to be straight from here to here. It can't rotate because, at B, it transfers rotation from one side to the other, and so there's no way to make this anything but flat. Right, now on the left side of the hinge, can there be any difference in rotation between the right side? No, it has to remain horizontal. Now, it can't have any slope, but it could move up and down because that's what the shear release is saying. So we'll just say no slope. And we'll just kind of leave it at that. We'll come back to it in a second. It could displace, though. Now, if this section, the middle section, can't have any slope, what do we know about the left section? Can't have any slope. It's impossible. Because the slope is continuous the entire length of this beam. The shear releases don't do anything. They don't allow any discontinuity in slope, right? A shear release does not allow this shape to happen. So if there's no slope on the right because of the fixed support, then there can't be any slope in the middle. Therefore, there can't be any slope on the left. So now we know no slope in A to the section cut, or to the point of interest, and because there's no deflection, this has to be flat and 0. Okay, so now there can't be any slope in between. Can this middle section move up? Yeah, absolutely. This shear release means that the left side and the right side don't have to displace the same amount. And likewise at B, the actual shear release means that the left side and the right side don't have to displace the same amount. And so here is the diagram, and this would have a value of +1. So it gets to be a little bit quirky with stuff like shear releases. Here, 0 between A and the point of interest, up, +1, back down to 0, and across. So probably the most kind of unique influence line that we've seen so far. Yeah, Ryan.
So whenever you have a fixed support and it's kind of cantilever but has a support only at the end, that's the only other discontinuity. For moment and shear, will that fixed support always hold through the entire beam for most occasions, or are there instances where it can lose the stability and it will have a shear or a bending moment in it?
I mean, I don't want to give a rule that sounds like it's applicable to like every case, and I think that's probably complex enough of a question where I couldn't guarantee it's always going to be the case, but let's just put it this way. I see a lot of mistakes with fixed supports because the slope has to be 0, and I see a lot of issues where people forget about that further down the beam. Let's just put it that way. Let's just put it the way that 0 slope here, how far that rule applies. I mean, if you have a hinge, that slope can be broken, right? That slope can be different on one side than it is on the other, but unless you have a hinge, that's never going to happen. Likewise with displacement. You can't change that 0 displacement until you've gone past a hinge, and because there's a rotation, the deflection can change, or if you have a shear release. So just kind of keep that in mind and be very careful about what happens on either side of either a shear release or a moment release. Yeah, Luke.
Could there be an instance where you have a shear release, but like say we remove support A,
Uh-huh.
still have a shear release at B?
Yeah, we couldn't. Yeah, and why couldn't we? So it's a really good question. If we remove the support at A, would this have been a valid system having a fixed support at C and a shear release at B? It's unstable, right? This segment here would just drop down, and there would be nothing to resist it. So I'll never give you, like I said, an unstable problem. I would never give you an unstable problem on purpose. If it is unstable, it wouldn't change the answer in the system for the problem. But yeah, I'll never give you indeterminate. I'll never give you unstable. So if you see something like that, definitely flag it during the exam. But chances are it probably is stable and probably is determinate. And that's the thing with these problems. I get that question a lot. Well, like, what if we change this support? Then it wouldn't make any sense. And you're like exactly right. It wouldn't make any sense because it would become either unstable or indeterminate.
So just to be
Yeah.
clear, so if we have a hinge at B, at the shear release, then the shear diagram will look like a triangle between the shear 1, and B.
So you're saying if we had so you're saying instead of a shear release, we had a moment release?
No, I mean a hinge right there.
Okay, so instead of the shear release, we had a hinge, like a moment release. So you're saying then what would the shear diagram look like for section 1.1?
Yes.
Yeah, great question. Yeah, so in that case, exactly right. This would displace up, then we get back to 0 with a diagonal line instead of a straight line going across. Exactly right, exactly right. And that would be a stable determinate system. Instead of having a shear release, if we had a moment release, this would be a stable determinate system again. It would just be different because a different type of release was provided at B. Yeah, Hannah.
So how would the moment influence line look for this kind of problem?
Yeah, so you're thinking about the moment influence line for section cut 1. Is that your question? Yeah, so let's talk about it. So what would the moment influence line look like if we're still focused on section cut 1.1? So we still have a roller at A. This is section cut 1.1. We still have the shear release at B. So you tell me, so what do we do if we want the moment influence line at section cut 1, what do we need to do? Add a moment release. So now I'm just going to put a hinge in here, and then I'll draw, it wants to rotate clockwise on the right of that hinge. It wants to rotate counterclockwise to the left of that hinge. And now we've got to figure out like which of those are possible. And so in order to do that, we need to draw all of our boundary conditions just like we did before. So no deflection at A, but it could rotate. No deflection at C, and thick horizontal line because it also cannot rotate. So let's talk about it. I mean, there's only really two options for the segment from A to the point of interest. Like, what are the two different shapes that it could be? It could be a straight line, absolutely. Or point 1, section cut 1, could move up. So those are kind of our two different options right now for A to the section cut. And maybe that's a good way to kind of keep track of it. Just draw like a light line saying, well, these are the two possibilities. Those are the only two possibilities that could happen. Because either this counterclockwise rotation that wants to occur can't, and we get a horizontal line, or this counterclockwise rotation that wants to occur can, meaning this has to move up because point A can't move down. So those are our two possible scenarios. All right, if we start from the right, what can you tell me about segment BC? It has to be straight and it has to be 0 because C can't move up and down. BC can't have an angle because C can't have an angle. So here we know for sure that's going to occur.
And one of the definitions about the about B, wasn't it that it can transfer moment? So how does this apply? Because I know BC is 0 for the moment, but it can transfer moment. So how is that 0?
Yeah. So B. Yeah. So the hinge can transfer a moment for sure. The question is like, how effective is like this hinge at isolating the effects? I mean, it's kind of like what we've seen with hinges before, whether it's a shear release or a moment release. It kind of like isolates one side of the beam like from the other. So basically what this is telling us is that, look, this segment BC like can't transfer a shear over here, and therefore the shear like diagram changes abruptly right there. And once we get this diagram complete, I think it'll maybe make a bit more, you know, we'll kind of have the same kind of idea. But yeah, so think of it this way. A vertical load over here, where does that vertical load have to go? If I were to apply a vertical load, let's just say 1 right there, where does that vertical load go? Where does it, like, which support does it go to, A or C? All of it goes to C. So if all of this load path goes here to here, it can't go this way. And the load path, like traveling, like if this wanted to go all the way to A, that's what is partly carried by moment at the section cut. So because this is not the load path, that's why you're not getting any moment here from a point load over here. It's because the load path right here goes all to C. Now, if some of it went to C and some of it went to A, you'd see some moment here due to a point load there, but that's not the case. So this is kind of showing you how the load path is maybe broken up. And so that's another kind of valuable thing to glean from these. So let's talk about, like, let's talk about both of these possible scenarios that we've kind of laid out. So here, if I wanted to get from this, so if we're talking about the horizontal line, to get from here, well, I have to, do I have to get back to here? I guess that's one question. Yeah, I have to get back to here on the right side, but on the left side, it can displace up or it can displace down. But it can't have any slope, and so it would have to be horizontal like all the way, right? with this, and that's because there's zero slope here, the slope has to be continuous over here, and so it would have to be horizontal as well. Well, what about like this situation from up here down to here? Well, actually, I'm sorry, that is not, that's one possibility. Maybe it looks like this, or what's the other possibility? Straight, like horizontal straight. I mean, this is a straight line too, but horizontal would be the other option, and then it would jump back down. So between, like, I'll call it Roman numeral 1, Roman numeral 2, and Roman numeral 3, which of those works? 3. 2 can't work because why not? Yeah, I'm showing a rotation that changes from here to here. That can't work with the shear release. The rotation on the left side of a shear release has to be the same as the rotation on the right. And 2 is violating that, so it can't work. Why doesn't 1 work? I mean, 1's kind of compelling because it's the easiest, right? But what's wrong with number 1? There has to be a rotation at this hinge that we added. That's one of the rules. The rotation on the right side versus the rotation on the left side has to have a unit difference. Well, there is no difference in rotation here. So 1 can't work either. So what about 3? So here I go up, and then I change my rotation. Is that okay? Going from A to the point of interest and to the right, can that change an angle? Yeah, why? It's a pin. It's an internal hinge. That's the definition, right? There's no displacement relative left to right, but there can be a relative change in rotation. So that works so far. Okay, so now I'm horizontal. Getting back down here, I'm changing, right, height, but I'm not changing rotation. That's okay for a shear release. So I can drop back down like that, and there we go. And so in terms of starting to calculate heights and stuff like that, right, well, or let me just put it this way. This slope has to be 1 to 1 for this to work, because the relative slope of A to the point of interest, the difference between that and 0 has to be 1, which is just means that left side is going to be a slope of 1 to 1. So that's a good one. That's a good one. I know I said I wasn't going to work through these problems like start to finish, but we kind of did it anyway. But that's not necessarily my intention. So this just means I need to make the problems a little bit harder for the exam, right? Yes, Ryan.
So I do have a question. On the diagram above, and maybe
Yep.
this is just something to like think about, like when we do like the methodology of setting these things up. Because there's no slope, even though you have a shear release, because we want to think that if there's a shear release, it's going to drop and raise, and the roller is going to allow it to rotate. But because you don't, is because there's no, because the fixed support is holding it in place. Is that what you were saying there?
Exactly right. So you're basically saying it seems like intuitively these horizontal lines should have some sort of slope to them, is what you're saying. Yeah. So you're exactly right when you point to the fixed support at C. The fixed support at C is why all of these are horizontal. And so that's actually maybe a good way to look at these problems, is that notice that every single time that we've had a beam, like a compound beam with a fixed support somewhere, it's kind of driven the show, right? It's been in control for a lot of the boundary conditions, like all the way across the beam sometimes. And so oftentimes we've started here at A, and we've said, look, there's a couple different scenarios that might work. But every time that we've started from this fixed support, that's always been the place where we can actually figure out exactly what's going on. Now, it might involve a little bit from the right to the left and then from the left to the right. But I think as a rule, it probably makes more sense to start where there's more boundary conditions. I think that will help you pare down the number of possible permutations more quickly. But either way is fine. And I think that what we talked about here kind of graphing out the possibilities and then looking at each of them and saying that can't work because of this, or this one can't work because of this other thing, so this one has to work, and I'll make sure that it does. I think that's a good way to go about it. And I don't care on the exam if you have light pencil marks like this and you cross out stuff like that. I consider this partial work, right? I consider something like this to be work that I can give you partial credit for. So don't hesitate, but just don't make it, definitely make it lighter pencil so that I can realize that, yes, you're showing that these were possibilities, but that ultimately you cross them out. And if you can tell me why, that's even more partial credit as well too. Okay, so the last thing that we had, I don't think we have time for, it was 16, 18. I don't have that up. We're not going to have enough time to kind of walk through it, but I just want to kind of reiterate a couple of things. The final exam is going to have two problems. You're going to have a virtual work problem. You're going to have an influence line problem. Now, for virtual work, I just saw today that I said you won't be asked to do any shear energy on the exam. I don't know why I wrote that, but it is on paper, so you're not going to have to deal with any shear energy on the exam. I don't know why I did that, but it's fine. There's enough to keep you busy without it, but springs are valid too, right? So springs, axial, bending, you need to be comfortable with all three of those. And are trusses a possibility? Yeah, you got a recommended problem or one or two using trusses as well. So now with trusses, we've only dealt with them with axial forces. So keep that in mind. But that's something else to make sure that you're comfortable with. Yeah.
Didn't you tell us last class that there's going to be a frame on the test?
Well, yeah, frame, maybe a combination of a frame with the axial members. I mean, I guess I'm saying pure axial members are fair game. Let's just put it that way.
So for chapter 6, it will be only beams?
For chapter 16, the influence lines, yeah, just beams, yeah, exactly right. We've never done it. Well, your book has a couple truss influence line type problems, but yeah, so let me just be really clear. For the axial, like truss virtual work, think of it this way. Is there a problem that could have like a member that is axial only, which I would consider to be like a truss member, and have other portions that are like a frame? Like, absolutely. So if you see a pin member with only forces applied at the ends, that's an axial only member. So there is a way for me to kind of Frankenstein together a frame with elements that act like a truss. All right? Well, let's put it that way. I'm formulating the exam as we speak, right? So with that in mind, two problems. The exam sheet is set. I apologize for the typo with the steps like 1, 2, 3, and 5, but I think that all of you can figure that out. I'll fix that before I print it out. So, but other than that, like I said, partial credit, like the procedure means a lot to me. Diagrams, procedure means a lot. If you give me all the diagrams, if you give me all these steps, and you don't actually calculate any values, that's worth a lot of partial credit. So keep that in mind as you're practicing, being very comfortable turning these into like 1, 2, 3, 4 step analysis on your exam, because that's where I can give you the most partial credit. If you make mistakes, identifying how you know it's a mistake specifically, not just saying, I think there's something wrong. If you can explain why, that can help a lot. And you've got clear ways to check your work. You've got really clear ways to check your work, both with virtual work and with influence lines, right? Influence lines, we talked about it. You do it qualitatively. You do your similar triangles to find your numbers and everything else. Then you do like one section cut with a point load at a specific location. You can check your work right away. And also with virtual work, there's the graphical method of integration. There's the integral form of integration as well too. You can check your work that way as well. So stuff like that means a lot. If you have time to check your work on the exam, I strongly recommend you do it. And you could even tell me, hey, I'm checking my work. Let's say you check a location that's not correct, but you're still checking your work. I can still give you some partial credit for something like that, even if you didn't catch a mistake. So if you're checking your work, be really explicit about it. I can still give you partial credit even if you still miss something. So keep that in mind. So I'll get this posted up to D2L or my YouTube channel by tonight. I am available by appointment. I don't have office hours set for Monday for you guys, but I'll see if I can open up some time. But I am available by appointment, so keep that in mind as well. And good luck with studying for the